egunon and ongi etorri guztioi. So today is a pleasure the colloquium that we are going to see today. But before introducing the speaker and these colloquiums, I wanted to tell you something about the colloquiums itself, the program that is going on, and something that we are going to do a small experiment today is going to be the first experiment of this kind about these colloquiums. So these colloquiums is called ECUR BASQ Quantum Colloquium. So this BASQ is the quantum initiative here at the Basque Country about the quantum research, and it's to bring people of high profile to the Basque Country to show us the physics about quantum here in like the person we have today. Who are the organizers about this quantum colloquiums? Is the university here of the Basque Country, and more concretely the Quantum Center that is here at the University of the Basque Country. There is also BECAM, is the Center of Maths here in the Basque Country, and is the IPC, the Donostia International Physics Center. What is the small experiment that we are going to do today? This is going to be streamed by the usual channels here at the faculty of the science faculty here of the university. But also there is another big initiative in Spain. It's called Quantum Spain. It's an initiative about quantum that is going to join today, and we are going to do an online broadcasting of this colloquium today, and hopefully there will be some questions also online, and we will follow these things. So this is a small experiment that we are going to do today. And now let me introduce the speaker today. This is really an honor and a pleasure to introduce you today. Is Rainer Blatt. He's professor at the experimental physics at the University of Innsbruck. And many of the things that I can tell you, I can go through the bio, but he's one of the leading in all these quantum technology that has happened from the 90s, about building all this community of quantum technologies. His expertise and the lab he's running is ion trap experiments in Innsbruck. He did the PhD in Mainz, and then also a postdoctoral research at GILA with the Nobel laureate John Hall. He has many distinctions and many awards. Just tell me, I wanted to tell you just a few of them, like the Carl Zeiss Research Award, Stenger Medal, John Bell Prize, the Erwin Schrödinger Prize, and so many others. And today, he's going to talk about this, the quantum way of doing computation, simulations, and measurement. Please, Rainer.
Thank you very much, Enrique, for this very kind introduction. First of all, I would like to thank you for coming. Good morning, and thank you for being here. It's a great pleasure to be back here in Bilbao and to talk about some of our achievements of the last years. What I would like to talk to you about is what Enrique announced, is the quantum way of doing computations, simulations, and measurements. And that's going to be the workhorse, as you'll see a little later, that we use in Innsbruck. Let me get started. This is part of the activity, as you will see here, of celebrating 100 years of quantum physics or quantum science and technology within the year of the International Year of Quantum Science and Technology, which was announced by the UNESCO, and if you find more here on this quantum25.org website. We are celebrating this year 100 years of quantum physics after quantum mechanics was first completely formulated in 1925. And this is actually also headed 100 years of quantum physics is just the beginning. And we are seeing now for a few years that we have learned so much about quantum physics in the last century that we now can begin to do advanced applications, to have advanced applications stemming from quantum physics that only appeared over the last decades. And I'll show you one of them, which is computation, simulation, and measurement. So the subject of today is that I start in this colloquium first with a brief overview. What are the progress of quantum technology? Why do we actually want to have quantum computers? I would like to talk a little bit about qubits and quantum registers, quantum gates, and some realization concepts. I'll introduce you to the concept of doing quantum computation with trapped ions, show you briefly the toolbox, and then a few examples how we do these computation simulations and measurements. And if there's time enough, I will also talk a little bit about how to scale the iron-trapped quantum computer up. All of this is, as advertised, done at the University of Innsbruck at the Quantum Optics and Spectroscopy Group, but also in conjunction with the Institute of Quantum Optics and Quantum Information of the Austrian Academy of Sciences. And also I'm a co-founder of this company that we have right now, Alpine Quantum Technology. And I'll come back to that in the end. And here's a number of sponsors that contributed, and without their financial support, all the research would not have been possible. So let's get started. A few quotations. You read in a popular magazine, Popular Mechanics magazine of the United States in the year 1949, which is only slightly older than I am, where a calculator on the ENIAC is equipped with 18,000 vacuum tubes and weighs 30 tons. Computers in the future may have only 1,000 tubes and weigh only 1.5 tons. I could not have come here to Bilbao with such a computer. So these times are over. But even in 1986, nobody else but Richard Feynman said we ought to be even more ridiculous later and consider bits written on one atom instead of the present 10 to the 11 atoms. Such nonsense is very entertaining to professors like me. I hope you will find it interesting and entertaining also. And I hope to keep you interested for the next 45 minutes on this subject. And by the way, if you really feel that you should ask a question, please feel free to interrupt me. It's easier to ask the question right away and to answer the question. So go ahead. So let's get started. If you just look at the progress in technology, computer development, we all are familiar with the so-called Moore's law. Gordon Moore is one of the founding fathers of the Intel Corporation. And what he did is he essentially formulated this law saying that if roughly about every 18 months the computer power doubles in a very empirical way. That's the original green line right here. And this draws essentially the numbers of transistors per die in a semi-logarithmic way as a function of the time. This served for a number of years as the roadmap of the semiconductor industry. So this law is not by chance, starting from the initial empirical drawing right there. Of course, the semiconductor industry had to project where do we want to be in the future. And in order to get to computers which are more powerful, you have to get faster, and that really means they have to get smaller. In order to get there, they have to develop machines like lithography and tools in order to get there. And of course, this served for a long while. But Gordon Moore already realized some time ago, no exponential is forever. Let me just show you in a slightly different way how this can be drawn. You can actually ask yourself in a classical computer, how many atoms do I really need in order to implement a single bit of classical information? And if you just see here, this is what was drawn. These are data, by the way, by Rob Keyes from IBM some time ago. These were micrograms, milligrams in the early 60s. And then, of course, it goes down. And I took the liberty to calculate how many atoms are used in these devices like the Pentium 4, 22 nanometer, and so forth. And it's rolling off. If you would take a very simple extrapolation, naively you would see immediately that already by the year 2017, a single atom had to suffice to really implement a single bit of information. We are long away from that, and it's very clear that well before that, you have to invoke the laws of quantum mechanics. So the question arises then, why do we actually want to have quantum computers? The generic answer to that one is there must be some application in physics and mathematics. But what are these? The entire hype that we see today started roundabout in the middle of the last, say, decade of the last century, 1994. Peter Shor came up with an algorithm that he could show if you had a quantum computer, factoring a large number would be much faster on a quantum computer than on a classical computer. On a classical computer, the efforts grow exponentially with the length of the number that you have here, where on a quantum computer, this only grows polynomially. By that time, it was clear this endangers some of cryptographic procedures like RSA, and so money was available to see whether that's true and whether such a system can be built. A little later, Love Grover came up with a fast database search Typically, on an unsorted database, you have to search for the number of entries right here. That's the number of draws you have to make, while on the quantum computer, this goes with the square root of the entry, number of entries, and that saves a lot of time. This is the so-called Grover algorithm after Love Grover from Lucent. The simulation of Schrödinger equations was hinted to already by Richard Feynman in the mid 80s, and I think that's a hot topic right now, and I'll come back to that a little later. Something that's often overlooked is that, say, a quantum computer can be used as an atomic state synthesizer. In other words, this really means that a quantum computer can be used to tailor certain states for precision measurements, and I'll come back to one example a little later, in such a way that you can enhance the measurement in a quantum way. And this is now used for quite a number of things, and this is going to be also one of the applications in the future that make real money, because sensors can be enhanced in a quantum way. Something that I added here is what we call as the quantum physics is now revisited with what I call the information-guided eye. What do I mean with that? When we just take computer science and information science, and we know things like error correction, entropies, or like Shannon entropies, and things like channel widths and so forth, are used to describe these things. Quantum error correction, I won't have the time to go completely into that, maybe in the discussion later on, but this is a notion that entered quantum physics, and we are rewriting textbooks not by content, by procedure. And the procedures that we use now to understand quantum physics is something that really, I think, is now a renewed way of looking at quantum physics. So there's a number of reasons to do that. But what do we need in order to get there? Now, you know, a classical bit is nothing but a switch, a classical state of 0 or 1, the position of a switch up or down. And the register in a classical computer is just a bit row with all of these ones and the zeros that we have there. The quantum bit, on the other hand, is something that we all know. It's just a generalization of a superposition of the two states. So you just write down your old-fashioned two-level system. And by the way, whenever you just talk about physics with two-level systems and go to a funding agency, say qubit. Funding is more easily obtained. Otherwise, it's old-fashioned. And we, of course, depict that typically on the Poincare sphere or the Bloch sphere as indicated right here. So you all know this. A quantum register, then, is just a generalization where you take the L of these two-level atoms and 2 to the L quantum states. And, of course, they correspond to a state that we write down, such as a direct product. And you see, there's a slight difference now here to that one, which is important. Meaning, we have to write this as a direct product, saying that essentially, if I change, say, this register in one position anywhere I do this, the entire information changes, whereas on a classical register, you just change the last position or any position right here, and the rest couldn't care less. The reason is, of course, that we have to write down the entire register as a general superposition, or meaning that the register is in an entangled state. And that, of course, speeds the system in principle up in the following way. We have very many computational pathways. So, for example, if you have the qubit number right here, then the computational path is exponentially grows, like the number of Rice cones that you double with each field on a chessboard. And you see here, these many pathways can interfere and produce the result. So you don't necessarily know where you put in the stones in this lake right here, but that non-local information, the superposition, is contained right here. And if you just put the finger of something right here, everything else is interacting, of course, in producing the interference pattern. So this is important, that you just change one piece right there. This is often called the quantum parallelism. But of course, nothing comes for free. You have to control all these things. There's nothing like a free lunch. This is the hard part, but once you can do that, then you can actually get that much of control. Okay, now, in addition of these things, we need, of course, operations. And the operations that we need are the following. Single qubit operations really means we have to start from arbitrary input states, and we have to be able to put that Bloch vector, as we call this, or the quantum information that's here indicated by this vector on the Poincare sphere, to arbitrary positions, and we'll be able to tilt it. These are what we call single bit rotations. They were well known, and we know how to do this. What was not so easy and was not recognized until the mid-90s was how to do the equivalent of the XOR operation, the Boolean XOR. The Boolean XOR simply states the following. This is the truth table. If the controlling bit is set to 1, the target bit is supposed to be flipped. But as you see here from the Brown-Ket notation, this is supposed to hold also for superpositions. And then this is, of course, a coherent operation. This is then called the controlled NOT gate operation, which is the equivalent in quantum mechanics for this Boolean classical exclusive OR operation. And it was shown already in the mid-90s that together this is a universal set of gate operations, meaning once you can realize these, then you can build already a full-blown quantum computer. So the recipe for a quantum computer is you start with a superposition, you have a quantum process, which you break down in a sequence of 2-qubit operations of the C0 type and single-qubit operations with not necessarily equal thetas and phis, that's the angles about you which tilt these things. Then you have, say, qubits lines that show the time development right here, and eventually you end up with a superposition of the qubits which are different in this way. Of course, this is completely unitary, so you can just reverse this, and you have not gained any classical information. So in order to get classical information, you have to project this, you have to make a measurement, and once you have the measurement, you get one outcome. Also meaning that, of course, you have to run maybe the quantum computer several times in order to get a statistical significant outcome of classical information in your register. But that's a small overhead, usually. Now, what are the various ways to implement this? And over the last, say, 2.5 decades, very many realization concepts have been investigated. Some of these things are described in roadmaps. The US roadmap is no longer continued, but holds enough introductory information if you want to look at it. The European one is still roadmap. The roadmap is still continued, and the latest version is here. Also, you'll find more information on these two, say, publications. This is the Quantum Manifesto of the European Flagship Initiative, and this is a more recent summary of the National Academy of Sciences in the United States. I will talk about ion traps. There's also neutral atoms in traps, optical traps, lattices, microtraps, neutral atoms in cavity QED, NMR liquid, superconducting qubits come in a number of flavors, charge, flux, and phase qubits, solid state concepts, spin systems, quantum dots, optical qubits, linear optics, quantum computation, and even some exotic things. I don't have the time to go through all of these. Just keep in mind, quantum systems are good for quantum computers if they can be controlled and manipulated in a superior way. You have to do that very carefully, otherwise if you cannot do this with high reliability, or as we say these days with high fidelity, then you cannot do this. Over the last, say, 10, 15 years, these are the dominating technologies. I'll talk about ion traps, but there are other approaches about optical traps, superconducting qubits, solid state concepts, and there's also some optical systems available. But I will concentrate from now on the ion trap. Everything else, what I said so far, is valid for all of these. Now come the specifics. The idea how to realize such a quantum computer with ion traps was essentially the first one, was really done and was conceived in 1995 by Ignacio Cirac and Peter Zoller. And this is the seminal paper where they just said, okay, let's just take a number of ions sitting right next to each other in a trap, and let's just point a laser beam towards these ions and do the manipulations. The main idea in that paper was, once you have the addressed lasers and single ionized qubits, the idea is to use the common motion of these ions to create the entanglement. I'll show you how this works in a minute. Since that was conceived and seen as a viable way to do it, there were very many other proposals that followed this in the just a few years after 1995. What is the idea? Now, the idea is essentially to realize that the NOT gate operation, and I'll show you in a minute how this can be done, because that then allows you, as we saw before, to realize a quantum computer. But before we go there, let's just talk a little bit about qubits with ions. Now, a qubit, as I told you before, is nothing but a two-level system. But a two-level system, of course, doesn't nicely exist in nature except for electrons. With atoms, you have to realize it, and this is usually done by optical pumping. and they have to be long-lived because you really want to have long coherence times. Here are the ions that are predominantly used. These are the alkyl earth elements, so they're hydrogen-like. And if you're starting with the calcium, strontium, barium, you see a lower lying D state right here. And that's an optical qubit, as we say it. And we have pioneered this in Innsbruck since the beginning. But everything else can be also used, say, for instance, in lower lying manifolds, like, for instance, a hyperfine manifold or the Zeeman splitting of the ground state right here. This is also two-level system that can be used. But then you have to replace the single excitation right here with the Raman excitation, but otherwise things stay the same. And this was then done in very many labs. You see here the pioneering labs where these definite species were worked on. But I will concentrate predominantly on this optical qubit. Anything that I'm saying can be readily translated to the other qubit, if you like. Now, a trap is a variant of the so-called Paul mass filter, which was conceived in the 50s by Wolfgang Paul. Wolfgang Paul came up with this contraption here. If you apply the right voltages with the right frequency, then you can guide an ion, a beam, through the system in a mass selective way. But you can keep these ions also inside when you wind electrodes around it so that the ions just stay in the center. These rings can be replaced by so-called segments, and this is a segmented trap right here, keep the ions in the center, or by tips, then you get a stiffer confinement. These are the developments that we made in Innsbruck. There's also hybrid technologies where you have segments and end caps to give this the confinement right here. And more modern versions then use now lithographically produced traps by projecting all these electrodes to the surface, and they are called so-called surface ion traps. Now, the trap that we are using predominantly in Innsbruck, and the first ones that we've used and still are using them to some extent, is depicted here. This is an ion trap where we have the distances between the tips right here of about 6 millimeters, and the lateral distance is about 1 millimeter right here. And you know, the trap is essentially a harmonic oscillator for, in this case, calcium ions, or for ions that you really want to store there. And as you well know, a harmonic oscillator is described essentially by the trap frequencies. And the trap frequency that we have here for a calcium ion in the center would be about typically 1 megahertz in the longitudinal direction and about 2 megahertz in the transversal direction, as you can see here, depending on the voltage that you apply. And that's all that you need to keep in mind for the rest of this colloquium. Now back to the Serac-Solar idea. We know now we can encode qubits in narrow optical transitions or Grondstein-Zeeman coherences. And then, as according to that paper, we write down the state vector of that quantum computer in this line. That is the most important part. What does it say? The state of my system is described by the internal degrees of freedoms of the ions that are sitting right next to each other, with the direct product of the number of phonons in the center of mass motion, and that number of phonons in the center of mass motion, that's the motion, is considered to be the ground state of the harmonic oscillator. So no motion at all. That's the idea, and I'll come back to that in a minute. So these ions are sitting stock still right there in the trap, and now you want to realize the CNOT gate operation. That really means whenever the controlling ion, let's say this one, has an excited state amplitude, then you want that the target ion gets flipped. But they are sitting right next to each other. Why should they know? And they, of course, they don't know. Why should that ion know that there's an excited state amplitude? The basic idea here with Ignacio and Peter was the following. You just take a laser beam pointed to this ion and map the internal state right here to a 1 of the center of mass motion. I'll show you in a minute how this works. What happens? Once you have a phonon quantized motion in the system, that particle starts to move. Due to the Coulomb repulsion, the entire chain starts to move. So from the point of view of the chain, it doesn't know where the phonon was put in. This not knowing is something that we describe as entanglement. Entanglement is a superposition of all these possibilities, so we don't know that. But I can go now to this ion with a second thrust beam and make a transition if and only if I had motion in the beam. And I'll show you how this can be done in a minute. And finally, you go back to the first one and then rewrite the 1 from here to a 0 into the internal degree of freedom, and you just leave the 0 as it was. That is exactly the gate operation that we need for the CNOT gate operation, and as the critical element to realize a quantum computer. It needs individual addressing with high quality, efficient single qubit operation, small decoherence of the internal and emotional states, and of course, eventually you need to realize the quantum computer as a series of these gate operations, as a sequence of these laser pulses. Now, this is the contraption that we use in the in our device, in our laboratory. You see, this is the ion trap, and we have beams going through this in order to cool these ions. Cooling these ions, let them align along the system right here, and then we also look for the fluorescence light that they scatter, and this gets then caught by the CCD camera, and here we are. So this is a string of ions, or a quantum register, which is a typical string. It's not typical in the sense that the best that we ever observed. It's really typical. We work with these strings every day. So we have now a quantum register. We can apply lasers to address the individual ions right here from beginning to end, and really entangle the system and then do all these operations. Now let's go into a few more details. What is the system? It's a calcium ion. The qubit is encoded in the ground state and the excited D state, so with a lifetime of about 1 second. And we are detecting whether the system is down or up there by shining in a laser light at 397 on this dipole allowed transition. And if the electron is in the ground state, it scatters a lot of light, so what we see is bright. If the electron is shelved, as Hans Demelt would say, into the D5 half state, this is not available to shuttle back and forth. The electron is not available here, so it doesn't scatter light, so we see darkness. This is what we call the logical up state, or the logical 0 state. This is the logical down state, or the logical 1 state. And this, of course, is the basis to see the so-called proverbial quantum jumps. We have a high detection probability for these individual states, and that's what we call the readout fidelity in such a system. Recap, we have this two-level system sitting in a harmonic trap. And of course, it's the direct product, so we have to actually write the Hamiltonian in such a way that we have many of these two-level systems, which are just different by the trap frequency nu indicated here, but the phonon number n, and the ground state and the excited states e, the electronic excited states. That, of course, immediately tells you that there are various resonance conditions for lasers that you shine in. So if you shine in a laser here on this carrier transition, as we say, then this does not change the phonon number, but of course it allows you to manipulate the Bloch vector or the quantum information, that's the qubit. But of course I can also shine in laser, for instance, on this transition, which just absorbs one phonon, and then the system, as we can show, predominantly decays to that state, and it climbs down the ladder until it finally resides in the state n equals 0. Remember, that's precisely the ground state of the harmonic oscillator. That's precisely the state of the vector that is the basis for the Dirac-Solar idea. Once we are there, then you can actually see there's no way that I can scatter light on the red sideband, but I can scatter light on the blue sideband, for example, and I'm left with exactly 3 transitions: the carrier transition, the sideband which adds a phonon, or the red sideband which eats up or absorbs a phonon right here. And these are precisely the operations that we need now. The internal superpositions are affected by the carrier, and the sidebands create the spin motion entanglement according to papers as you can see here. So that's the mathematical basis. Now we are ready. We can do quantum information processing according to that recipe by writing down a quantum circuit, which are implemented by gate operations, at least of the single qubit operation and 2 qubit operations of that type. And again, these operations are all realized with carrier and sideband operations. Predominantly we use the blue one. We can also use the red one, and sometimes we are doing this, but this is typically what we do. Then the question is, what do we measure? Measure is something you can do with the ions. You see whether the system is excited or not by doing the shelving measurement. But of course, you also want to know whether there are some possible coherences between 2 different of these ions. And then you do something that we dub tomography, because you're just measuring and see whether the string of ions shows an upstate population. But prior to the measurement, then you do, say, rotation of the first ion, measure again, then you do a rotation of the second ion. You see all of these measurements, not just sigma c, but sigma x and sigma y. And then you get the so-called fingerprint, finally, showing you density matrix information on, say, here the coherences are the off-diagonal ones and the diagonal ones of populations, and here the imaginary part should be the zero. This is a fingerprint of the Bell state, for example. This is the way we do these measurements. There's also a spectroscopic way of measuring entanglement, but we won't use that today. So let me summarize the toolbox. The toolbox operation is such that you have these ions sitting side by side. I can shine a laser along the axis, affecting all of them simultaneously. For example, with the resonant manipulation, you can just tilt the Bloch vector by pi4, pi/4, pi/2, or pi pulses, or whatever you want. And these are operations that take a few 10 microseconds with a high fidelity. And individual operations, we usually in an off-resonant fashion because we want to minimize the crosstalk to the neighboring one. So we just take stark shifts right here. And this is also operations that work fast with very high reliability. The entanglement was supposed to happen via the motion of a Dirac-Sola idea. We are using now a more modern version, which is what we call a Mellmer-Sørensen gate operation, but it also involves the motion of the system intermediately. The reason for that is the following. The Dirac-Sola idea is very sensitive on whether you are exactly in the ground state or not. So if you had, say, an excited state amplitude, then all of a sudden the system can become somewhere in limbo, and some imprecise operations can happen. So you want to make sure that the system always returns to the exact ground state. But this is not necessarily the case here for the Mellmer-Sørensen gate operation. This is using sort of a two-photon transition. When you shine in, say, the red sideband and the blue sideband simultaneously, then you can make a transition, say, from both ions in the ground state to the excited state, and you make a superposition. But there are many pathways, because first you can just create, say, an excited state of the first ion with a lower phonon number, then add a phonon number to DD right here, or you can absorb this on a higher phonon number and then the lower one, or you can go to the second ion. So there's 4 pathways. And as you know, spectroscopically, in a minute, from a good 2-photon transition, there are first order Doppler free, so they're insensitive to first order with respect to the motion. So in other words, unlike the Dirac-Sola idea, which is very sensitive to the fact that you're recurring to the ground state, this will do the entangling operation in spite of the fact that you're not perfect in the ground state. So this saves you some of the operations. There was a question. F2 is the fidelity of a 2-photon transition. Of the 2-photon, here's F is just single, the F2 is just the fidelity for that. And we have also fidelities for F3, 4, 5 when you have more of these ions. Okay? Good. So we have now another system of universal gate set, and these procs realize that. We have many more operations, and I won't go through all of these details, just for those who are mathematically more inclined. Of course, all of these operations can be written down as unitary operations. For the rest of this colloquium, I will use only these, say, box, or this color code description, where the unitaries are described here by the boxes on one line or many lines. And you see here, this is this local Stark shift when you apply one off-resonant beam right here. This is a collective Stark shift, so you apply to all of these qubits simultaneously these things, then to the collective Stark shift right here, or the collective Stark operation when you do this with respect to a different angle that you can write down in a more general way. And then finally, the collective operation with the bichromatic beam, that is written down as a spin-spin interaction right here. Keep that in mind. So that's an entangling Mellmer-Sørensen gate operation. We have a few more of these things, and I don't have the time to go through these things. We can hide one of the lines, for example, by storing that population in a different Zeeman state, so it doesn't participate in the operations. As such, we can reduce or enlarge the computational subspace. We have dephasing operations, so we can actually open systems. If you want to do that, we have initialization and reset operations, and we can even store both amplitudes of the qubit in 2 hidden states, such that we have a cache memory. While we do operations on the entire register, we can hide a qubit for a little while. So all of these things are available and, of course, are used in the operations. Okay, so let's go to the lab now. This is how it looks in a lab. This is a quantum optics lab, and you see here lots of lasers, and this is where the ions reside, and of course everything is steered here from the classical computers. And we have done very many of these algorithms. I don't have the time to go through all of them. I would like to go to the last three of them, just show you an example of what we do. And when you start with that, some of you may know how it looks like. It looks like a complicated optical setup that is then applied to the ions, and you need to control all these things in detail. That's getting very tedious if you really want to do computations, and definitely not something that you want to hand out to a mathematician who really wants to do calculations later on. So we developed a smaller design. We put everything in these two 19-inch racks, and starting from these modules, lasers generation, trap module, and so forth. So that's the original sketch, and all these optics elements are now in drawers, hidden, so that you don't have to worry about these things. This was achieved in the Action consortium of the flagship initiative of the European Union by Christian Marciniak and Ivan Pogorelov in our lab. And this is the trap module as we have it right now. That's what we call a quantum CPU. And this is internal. It's still a trap like the one that we had before. The size of the trap is only a few centimeters internally, and everything fits nicely in that drawer. And this is how it really looks like, and this is the big consortium that achieved that. So this is now routine in our laboratory. Let me just now show you three examples. When we want to do a computation, or a simulation for that matter, we have various ways. So for example, we write down a Hamiltonian, and that's too difficult to calculate in a classical computer. Then you go to a quantum simulator. That could be an optical lattice, could be superconducting, could be an ion, whatever you have. Then there's essentially three approaches. The first approach, which is really highly successful these days, is an analog simulation, saying the following: you start, say, with an initial state, and then you really implement your Hamiltonian in terms of a unitary, that's how you write it, and apply that to the qubits and simply wait and start to look then at the dynamic evolution of that quantum state. And from the dynamics, you can derive then all the eigenvalues and the energies that you need. You can derive everything you need. But it requires a match between the engineerable interactions, how you do that, and the model that you have. So it's not always easy to do, and I'll show you an example in a minute. A real computation is done in a different way. This is actually a digital, what we call digital quantum simulation. That really means the entire process is broken down, this unitary, in this sequence of gate operations, which are sequentially applied to the system. You can simulate any model, but it requires typically very many gate operations. And if you have errors which are not corrected for, this runs out of steam. So that's the drawback, but this is actually a typical computation, although it goes on the digital simulation. And there's a hybrid one. The hybrid one, of course, is useful once you're not so much interested in dynamics, but say in steady state values. Then you just have your Hamiltonian, for example, living in the classical computer, and the Hamiltonian, the computer simply says, okay, I want to see whether my expectations from my Hamiltonian really match what I get out of a quantum register. So it comes up with a set of parameters, applies these, taps into the Hilbert space provided here by an analog quantum simulator or generally by a quantum register. And you don't do the computation in this register, but you just measure one value, say an expectation value. Feed this back to the classical computer, which is able to calculate from that, is that matching the expectation that I had from my original parameters? If that's not the case, you just go around and iterate until it does, then you have found the value. And this is helpful in some cases where you cannot do any other calculations. So these are the three different approaches that we typically have. Let me just give you a digital approach. This is, of course, rely on the fact that you write down the Hamiltonian as a series of sub-Hamiltonians, and then you approach each individual unitary, the difficulty arises from the fact that they don't necessarily commute with each other. Then, of course, you just replace this by the individual one and apply this for a time slice t divided by n. And one can show, and that's the so-called Trotter-Zubik approximation, that then the dynamical behavior of this approximates the entire unitary evolution of the system, the finer the slices go. So I find more about these things right here. The analog simulation, on the other hand, requires a match of the engineerable interactions. So suppose for a minute we come up with, say, a bichromatic beam from the side. You remember from the translation table that I gave you, the bichromatic beam is a Milnor-Sørensen beam that gives you the spin-spin interaction. And if I detune these lines in addition, which I can simply do with my lasers, then I create a Stark shift. But this is now written in a fashion that you all realize this is nothing but the Ising model that we have in solid-state physics. So just applying this interaction in such a way immediately gives me an analog implementation of that Ising model, and I simply can apply it for a certain amount of time, wait, and then see how the system evolves. And these parameters can be adjusted. You see more details in a nice review in a recent one by Chris Monroe. Just to give you an example, digital simulations right here, we performed this on various Hamiltonians a long time ago. These are early measurements, you see. The solid points give the measurements and the open points the theory. And then you see this runs out of steam after so many phases right there, so many pulses right here. The reason for that is simply that at that time, and this is still true to some extent today, each individual gate operation has some errors, and they accumulate, and then you run out of steam. But nevertheless, you can see from the dynamical evolution, make a Fourier transform, you find the frequencies, you find the energies, you can see all things that you see in such a system. We can do that with many more complicated ones. This is, for instance, an example of a 1D lattice gauge theory. It's a Schwinger model, which describes the pair, the antiparticle and particle pair creation. And you see this is writing down this by absorbing all the gauges. The details don't matter. But in fact, what you write down, you just take this Hamiltonian, take the translation table, and then you rewrite things in terms of gate operations, apply this 4 or 5 times, and then you see here the various measurement points, and they nicely match within limits what the theory describes this. For this, of course, easily calculable. And you see here, depending on our notation, we have created a particle-antiparticle pair at this point, sort of a Rabi flop in this description, and this nicely describes this the evolution of such a Hamiltonian. The analog simulations were done by us and also by the group of Chris Monroe, and you see here the phase transitions that have been nicely studied. So, for instance, paramagnetic to ferromagnetic crossover and the Néel ordering. This is a large study of the Monroe group. We have done things also for the Ising Hamiltonian, which is then in the limit where we have a larger detuning right here, a flip-flop Hamiltonian. So we just make a quench operation right here. So we start with an inversion and then let the system go and see the ballistic evolution of the spin in this system. Now the magnetization evolves and entanglement is created. And this is done now in a tunable way. You can actually tune the interaction lengths for these things. There's many, many things possible. This allowed us to do, for instance, quantum transport simulations. So we just take the XY Hamiltonian and add this order by just having, say, different Stark shifts at different places in the spins. What happens then is the following. This is, again, the ballistic transport that we expect to see in the same feature right here. It's just more ions here. But if you add this order, we get Anderson localization, so we can simulate that. And then we can add also noise to that disorder. We just make it less noisy and a bit more noisy. Then you see there's a diffusively enhanced transport in the first place. But if the noise really gets too large, we already make a measurement here. So that's a quantum Seno effect that's absorbed of it. It's a diffusive suppressed transport. All of these things can be done. And in fact, you can study even the hydrodynamic behavior. So when you see Levy flights, when the system evolves very largely, then you can see all these kind of statistics. All of these things can be studied in the very same simulator, analog simulator, just by reprogramming it. And finally, a hybrid simulation right here. Take again the series of Hamiltonians that we write down as indicated. We go to a classical computer, taps into a quantum simulator or the quantum register, and then the system is fed back. We take here, as an example, the Schwinger model again. We want to understand, we want to measure the ground state, so it's the steady state, the system here with 20 ions. This is, again, the energy that we measure, the expectation value, as a function of the iteration number. This is, I call this a fly sheet plot because there are so many dots which do not fit. The point simply is the following. In order to make optimization of the number of parameters right here, you have to find in the hyperdimensional space a minimum. And you don't want to get stuck in a local minimum, so we just have added the stochastic component. But then you see in a Bayesian estimate, we nicely approach the quantum state, which is here the dashed line. That's actually the state that we calculate, but we are getting close to it. And of course, the question is, when do you stop? Usually you stop when your resources are finished, but then how close are you to the real state? And this can be measured. This is sort of a self-verifying process. Instead of programming the computer to calculate the expectation value, you can also program it to calculate the variance. And from the variance, you know, when this goes down to 0 or very close to 0, then you know, yeah, I found an eigenstate. So this is a nice feature that can be used. And these are the typical algorithms that are now used, for example, in quantum chemistry calculations. We did here a calculation on hydrogen molecule to find the ground state right here and the potential curves with very high accuracy. The same was done in the group of Chris Monroe with water molecules and with other light molecules. You see here, these things are now done. Of course, these things are all toy models. A real molecule which deserves to be calculated for reality is beyond what we can do. But it shows the way towards we can go and what we can actually do. So it's a demonstration. This brings me finally to the quantum measurement, and I would like to conclude with that one. Optimal metrology was investigated in our group here by the experimentalists, and by the ideas were born out of the group by Peter Soller and Raphael Kaubrücker. And this comes back to ideas that I discussed with Peter Soller a long time ago. Here's, for example, a precision measurement of the frequency difference in our qubit, which essentially is an optical clock. And this is typically done by a so-called Ramsey sequence. So we just have a pi/2 pulse, we just put in the coherence plane, let the system rotate, and then the second pi/2 pulse goes, depending on the phase, up and down. And that's precisely what we see here. And this measurement can be done, of course, in a refined way. So you can actually find the measurement center very nicely. And this is a more the recent summary that we made, the last precision measurement. So this is the optical frequency standard that we have. In principle, this can be down to 10⁻16 and better. So this is how you improve these things in optical frequency standards. Now, the question is, can we generalize this? Can we actually learn and can we improve this by using quantum techniques? This is, again, picturing a simple Ramsey experiment, a single ion right here, pi/2 pulse, free evolution, pi/2 pulse, measure the excitation. Can I enhance this by using more ions? Of course I can, because typically I get, if I have more ions, an enhancement by the factor of square root of the number of n that I have, just by just averaging over an ensemble, statistically non-correlated ensemble. But I do have the point here, I can correlate these systems by just having the right unitary operations. I can create correlations, I can create entanglement. And so the idea was here we have an encoding unitary here and a decoding unitary here, not just a pi/2 pulse, but we can leave this to an optimization by a computer, capital theta and the lowercase theta right here. So we just measure, for example, first the total excitation, then we just let them free running as variables in a computer, find another unitary, go back here and see whether we can better measure the entanglement or the center frequency of the system. And then, of course, we iterate as we did it before in a variational quantum simulation. Now it hinges only on the right formulation of the cost function. So in other words, we have to define what the problem is. We want to estimate the interferometer phase right here from the measurement record. Essentially, it's a Ramsey interferometer. Then we calculate the mean squared error and make some Bayesian estimate based on initial distribution, and then we minimize the measured imprecision, that is the variance, and then we try to optimize the performance. Now I'll show you how this works in principle. Suppose you had a simple Ramsey measurement where this second pi02 pulse is just shifted by 90 degrees out of phase. So essentially from the cosine that before you see a sine. Essentially you want to stabilize the interferometer at this point, that's the center frequency. You're limited always by projection noise, that is just a noise of a two-level system, that's what you get here. And the prior distribution that we get is just what you expect from put into your Bayesian estimate, that's the prior distribution. Now, when I just have the numbers here, 0, 0, it really means this is a classical coherent spin state, meaning that's pi/2 pulse, another pi/2 pulse, just for the notation. But I can do now, first of all, a Milnor-Sørensen gate. The Milnor-Sørensen gate creates a so-called squeezed spin state. So I just get a smaller variance of my distribution on the Bloch sphere, and then can the system let go. So what I expect when I rotate the system, I get less noise. I have already some improvement. Can I improve anything beyond what is expected? The noise measurement right here, that's the minimum that I should be able to get. And the question is only, what do you want to improve? Now we can do better, and what we can do better is the following. I can just enhance the dynamic range of the entire interferometer. I can make this linear. The slope is not as big, but the catching range is bigger, and the system gets bigger by, say, a tailored measurement. Unfortunately, right now, I've traded off for the larger dynamic range. I've traded off some noise. But here, I have optimized only my output, my measurements, my readout stuff. That's what the 2 really means. But if I just do now, say, a tailored input and a tailored measurement, then I can see this dynamic range has increased and the error is almost as down as it is expected from the spin squeeze state right here. In summary, what you get here, you're close to the Heisenberg limit, that's the optimal quantum limit that you get here, and you get the enhancement as the number of ions grows. Here it's only 16 ions, but suppose, for example, someone like Junier has now 10,000 atoms in an optical 3-dimensional lattice. That's a huge enhancement that you can get in principle by just following such a protocol. And this is precisely where quantum measurements using entanglement and using the controlled entanglement in this ways can improve the interferometers for precision measurements. This is not only valid for frequency standards, this could be done for magnetic moments, for magnetic measurements, and for other things as well. I'm at the end, so let me just briefly summarize what are the goals and strategies if we want to scale this up. Now, of course, we need more qubits. For this, we have developed 1D traps, and now we are on the verge of controlling this to 2D traps. We need better control. We need quantum error correction. That's no way. We need also the computational power. We need quantum software. This we have to find a key problem to solve that can be solved beyond the ones that are out there already. And we need what I say predictability. If you want to go to a, say, commercial quantum computer, we have some companies around to offer that, and they tell you, okay, if you do the operations, you expect that many errors, that's the fidelity that you expect. But very often, when you just calculate then what is the result that I expect and what's the validity, and that doesn't match your expectations. You cannot predict. The reason for that is that the error propagation is not necessarily clear in these systems. And so we need to go from what we call the component error to the error that we go to the system performance. And that's something that's not easy. We have our models and we have done that to a certain extent, but this is something that we need for controllability. Scaling down really we need to miniaturize control hardware. You've seen we put everything in 19-inch track, that's one thing, but errors need to be protected against, that's passively done, but also in an active way for error correction. And we need faster gate operations. They can also be done with ions. There's a different story, but we can talk about this in the discussion. That needs to be done in all of these implementations. And finally, what I call scaling out means we need distributivity, meaning that we have a modular design, some optical interfaces, and some hardware with which you can interconnect these various designs. And also, you need quantum parallels processing software that actually does it. All of these things are necessary. I don't have the time to go through all of these details. I could go on for probably another hour, but the chairman is already looking at me. So let me just briefly summarize the current work and the developments. We have done quantum error correction. We have logical qubits comprised in several qubits according to what we call a color code right here. We know how to measure these syndromes and to correct them. We already have implemented fault tolerance, which really means we know how to suppress error propagation in such a larger system, and we can correct for qubit loss. All of these things are go under this, what I call keeping a qubit alive, at least for the time of the calculation. This needs to be done, and I think all the details are here, and some approaches in superconducting qubits, people have some good progress made, but it still is necessary to get everything done in a single device that's still open. For us, we have designed architecture of traps, so we want to have, say, two-dimensional traps. We have shuttling processes right here, but these shuttling processes are necessarily to be kept to a minimum, so we call this a quantum spring array. Also, we want to integrate the trap with electronic and photonic structures. We want to interface the ion qubits with photons. We have done that as a proof of principle, but that needs to be done also on chips. And then, of course, we use the ion trap systems for quantum networking. And the new developments in our lab involve also QDITs. That's using more levels than just 2 out of the manifold here, the Zeeman manifold, and that just boosts your Hilbert space with the same amount of control that we have, and the Hamiltonian learning entanglement characterization is stuff that we work on right now. With this, I'm ready. The dream is this. The dream is this, to have a trap, let's say a lithographic layout, where we have a group of ions that are comprising a logical qubit. They are interacting with each other, say with double-double interactions on a chip, or charges, whatever, or with ion cavity interfaces in a network. And then you can actually get very large devices. There's no reason against it. But let me conclude. There's a lot of fiction around here. When you just look at the press that we get and others get, and there's a hype around this, you find the Time magazine of 2014, but the latest version of 2023, you find statements like quantum computers will replace classical computers. Quantum computers are better than classical computers. Quantum computers are always faster than classical computers. There's a big question mark. And so let's forget about this, and let's just summarize the facts. The facts are, first of all, quantum computers are universal computers. They work completely different from classical computers with superpositions and entanglement. That information is much more volatile than classical information, but the good news is quantum error correction works. It just needs to be done, and it needs to be seriously done, which is not the case yet. And quantum computers are faster than classical computers, but only for certain well-adapted processes. Anything that has to do with, say, quantum features, for example, in a molecule, or for a certain optimization whenever it comes to signal processing, things like that, this is where you win. But you don't win for big data, for example, and other things. And of course, quantum computers are already reality. I've shown you the ion trap quantum computer, the superconducting quantum computers are ubiquitous, but there's photonic ones, and so forth. That's all fact. But fact is also that we have currently, say, a few hundred qubits available as in other devices, and we have about 500 to 1,000 gate operations available, but competitive applications need on the typical, say, 1 million qubits and about 1 billion gate operations. There's a large gap, and some of the people say, okay, you will never succeed. Some others say, no, we have quantum computers around the corner. Both ends are not true. There's a large gap. The good news is there's no physics law, there's no physical roadblock inside, there's nobody that there's this never going to work. That's the good news. So we just get started and do things, and then of course we can go beyond what's currently used in this computer. And then of course there's things that can be done today. Other things right here have to wait a bit more. This is of course the holy grail, for example, machine learning, logistics, all the stuff. There's a long way to go. So let's see where we go. All of these things can be achieved. Don't forget, keeping a qubit alive is the holy grail that we see right now. All of this was done, of course, in a big team. This was not done by me. And of course, we had a very, very big help. Without them, it would not have worked, with lots of people right here. Among them, you see here a local face, and there's another Spanish person right here, Miguel Angel. Without them, it would not have worked, and without them, this would not have been done. And here are the names. And just to finish, this is where we are. This is the airport in Innsbruck. This is the city of Innsbruck right here. This is the home of the quantum computer, made by AQT, Alpine Quantum Technologies. And now it looks very professional. 219 tracks, you can buy that. We have actually sold 3 of them to supercomputer centers, and that's the interior. That's what it looks like. This is the trap module. This is a 1 Hertz laser frequency. It's all done, engineered perfectly well. If you want to buy it, contact Thomas Mons. It's proudly made in the Tyrol, and I would like to conclude with a picture of this CPU. It's so beautiful. Thank you so much.
So now time for questions or comments, and please tell me also in the online if there is any.
Hi. First of all, thanks for the talk. I really enjoyed it. I have a bit of a philosophical question, maybe. Some time ago, I attended this fireside chat debate on the prospects of quantum computing, and most people seem to agree on we are following something like a Moore's law. So they were trying to predict the times for useful applications where we would have a quantum dot date and so on. But the interesting part maybe is that I happen to be sitting next to Didi Leifried, and he had a much more of a cautious point of view on it. He compared the evolution of quantum computing more with the evolution of airplanes, and he thinks we are in something like in the Renaissance with this Leonardo da Vinci and people like that doing these beautiful designs. But he kind of thought we still need a big revolution until we get this big jump for a fully working quantum computer. So I would like to hear your point of view, and if it's an optimistic point of view, whether you are, as a ion trapper, a hardliner on it, or you think maybe other approaches have also a chance.
You remember the slides that I've shown you in the end, the last few ones? There's a big gap, and the best thing would be to have, say, a completely new technology that we haven't come up with yet, that just fulfills all these purposes. It definitely is not so that we just have a technology and we have to go to a company now further develop. It's not engineering. There's a lot of physics to be done. So I'm not convinced that the technologies that we have will come up with, say, quantum computers that people would really like to have. Say that's 1 million qubits and say 1 billion gate operations, because that's technologically difficult, but it's not impossible. And now the question really is, do we have within these technologies possibilities to control them that far? And I think to a certain extent we can. I believe that we can just enhance this over the next decade from, say, a few hundred qubits, say, to 10,000 qubits at the least. That's something we can do in a modular design. I do not see any roadblock. But the question really is then, can we go beyond that? Is it actually necessary? Yes, for some applications like chemistry, it is necessary. But for other applications which are intermediate, like say physics, correlation functions, and didn't have the physics, there's other interests. Can we do quantum chromodynamics? Can we do, say, series calculations in physics that are not so much interest for the public, but there are physics interests, for condensed matter and so forth. I think we can come up with solutions that are very interesting and highly motivating for physicists to go there. Right now, we unfortunately see a big hype because of these newspaper articles, and some of our colleagues who are not very honest about this, they promise something that cannot be kept. This is going to be the supercomputer of the future, and this will replace everything. That's nonsense. We just have to make sure that the tools that we are developing see the progress, and that we actually go for the goals that we still have to do. There's also something really lacking here. What is the problem that we need to calculate? Do we have an appropriate problem that we want to solve? with the quantum computer? Yes, there are a few, but there are very few algorithms that actually work. So let's find out algorithms. That's motivating on the other hand. Let's find a different technology. Let's advance the technologies that we have, because for measurements, sensors, and for, say, intermediate solutions, like I said, condensed matter problems, in physics problems, there's a ton of interest that we actually want to follow. I agree, we will not make competition for the IBMs and the Fujitsus and the big computer companies that are around here in the near future, say the next 5 to 10 years. But for some specific problems, we'll make a difference, and there is no law that tells me it's not going to work. It will work.
So, yep. Here is another question, but I remind the people that is online. We are checking now the YouTube channel, so please put the questions on the channel, because we are following that.
Thank you for the talk. So I have less of an so I'm not an expert at all, but I didn't understand when you explained the 3 modes of computation, like this digital, analog, and hybrid. I didn't really get the difference. So in the analog one, you mentioned that you have this Hamiltonian you want to simulate, and you, like, I don't understand how you, from the operations that are available to your architecture, how are you reconstructing that Hamiltonian you want to emulate, if not breaking it down and then reconstructing it?
The analog idea is the following. There are analog computers. They were done many, many times before in a classical way. You have tooth wheels, and you just adjust the right thing. You just turn a handle, and then you just get results. What we do is here, essentially, we try to mimic the interaction that is described by a certain Hamiltonian. And the example that I gave you is an Ising Hamiltonian. The Ising Hamiltonian says, okay, my spin system that I have, for example, that has interactions with that spin with that one. And if they are different or have different angles, then of course they are different interacting. And the question is, how do they propagate? How do we study this? And what we have in our system, our Mermer-Sørensen interaction, I didn't detail on that one because it would have taken me another 20 minutes, can be written down as a spin-spin interaction. The entanglement that I create with this bichromatic light is a spin-spin interaction, formally. That's the translation table that I gave you. Also, when I just apply a laser beam in an off-resonant manner to a 2-level system, this can be described as what we call an optical Stark shift, as a sigma C operation. So formally, whenever I have, say, the Ising Hamiltonian, I can rewrite this in terms of that operation. So I just apply my bichromatic laser beam in a detuned fashion for a certain amount of time. And then the dynamics in the spin chain is exactly the dynamics that's described by an Ising Hamiltonian. In other words, if I just now stop it at a certain time, then I see, where are the spins? And I see the dynamical evolution. From that, I can infer everything that I want. The downside, of course, is this cannot be error corrected. If I make errors in my application of my things, then these errors propagate. That's the downside. Analog simulations cannot be error-free. Whereas what I put in slices with unitaries, if I just make an error correction after every unitary, then I can propagate these things without errors. So that's the difference between them.
So then the analog operations that are available depend on which specific quantum computer you're using, right? So like, it's not that maybe your computer can do this analog computation, but another architecture that's completely different.
That depends a little bit on these things, but of course these things are sufficiently general that you can use, say, Mermer-Sørensen also on superconductings or on other machines, or you can do this. They have other toolboxes, but of course, whenever you write down your gate operations that you have in what we call the Pauli notation, that's what I did here, then whenever you have that, you have a translation table, you can immediately translate that. And that's what I meant when it says, okay, I need a match between the engineerable interactions and the system. That's what it says. Yes?
So I have another question. So one of the algorithms that work in a quantum computer is Shor algorithm.
Yes.
Do you think how far are we for being able to factor from 2,000 to 4,000 bits is what is currently
we are far away from that. Just to give you a number, the latest I heard, we have done Shor's algorithms. We know how to run it, even in a scalable way that works out. But if you want to do it, say for RSA 2048, say 2048 digit number, it would probably take 1 million qubits and more than 1 billion gate operations. Yes. So at this time, forever.
Okay, so we actually had a question online, which then was later erased, but it was by Javier Mas, and for those of you who do not know, Javier Mas is in charge of the talent part of the Quantum Spain initiative, okay. Right? So it's.
So what's the question?
Oh, he was. How many logical qubits could you implement?
How many?
Logical qubits.
Right now we are implementing 2 to 3, and then it depends on the further development of the modules that we have. We are our internal roadmap goes up to 10 logical qubits within the next years, and then we'll see.
And then he further asks whether, in your opinion, the Microsoft Continuum is the standard.
The what?
Well, Microsoft Continuum is the standard for this kind of.
Microsoft?
Well, his question is the Microsoft Continuum? Sorry, I was misreading the Microsoft machine.
There's no Microsoft machine.
That was my impression.
There's no Microsoft machine. In spite of what they said, there was
MS Continuum got 12 in 56. Continuum.
The Quantinum?
Yeah, because the famous claim that they have 12 logical qubits in 56
That's right,
physical qubits.
That's what I told you this morning. They have 56 qubits, but they don't have logical qubits so far. They have wonderful fidelities, that's what they can do. Because they have so-called double qubits, they use 2 species. They use, in their case, barium and deuterium. And because one is used as the carrier of the qubit and the other one's used to cool. And then they always shift these two ions parallel to different sites. That shuttling, as we call it, takes a long time, but they have very nice gate fidelity, but they don't have more than 2 or 3 logical qubits at this time, according to the real encoding. What they sold as 50 logical qubits was, let's put it that way, someone would say fake news.
An exaggeration?
Any other questions? Sure.
Hello. Yeah. So I have a follow-up question. And I want your group's perspective on this regarding quantum error correction. So what you do is you introduce redundancy in physical qubits, right? And then you get effective logical qubits. So what will be your ballpark best guess that if we take the ratio of physical to logical for practical applications?
I'm not sure I understood your question right. You're talking about logical qubits in the first place, and then?
So when you implement these quantum error correction schemes, so you have this physical hardware qubits, and then you implement this, you get the effective logical qubits. So that the question comes to the ratio, physical to logical.
Yes.
So what will be your ballpark best guess for real practical applications?
The practical applications of the logical qubits or the practical application of the error correction?
Logical qubits.
The way we do this right now, we have error correction. We are using the so-called color code by Michelangelo Valentini-Gado and Hector Bombin, which is what I call a transversal operation. Transversal means that we can break down the operations needed for the encoding in a, we can break down the, say, the operations needed between 2 logical qubits to the same operations between 2 adjacent physical qubits. That's what's called transversal, so we can do it in a parallel way. So that's the dream of the implementer. It's not as good as maybe the surface code of Kitaev, but that transversality is for implementing things much better. That's why we chose it. So with this code, we can, at this time, do the error correction protocols with 10 qubits. We need 7 for the logical qubit, plus 2 ancillas that carry the error syndrome, and we have an additional flag qubit which is raised just in case the error propagation goes completely wrong, so that protects against that one. Now, in order to break even, meaning that we meet the error threshold, we need, the error threshold is on the order of about 10 to minus 4, roughly, maybe a little higher, but not much. And so in order to get below that, we probably need at least 13 qubits for the color code, if not 17. So typically, my guess at this time is that we roughly need an overhead of, say, 20 physical qubits for 1 logical qubits. At most 50, but I don't think that we can probably do it within 20. This is my guess from what we have at this time. Then this is the algorithm that we have, and then we just have one module which consists of, say, 5 to 10 logical qubits. That's the dream that I want to have in parallel. And then we just have to interconnect these logical qubits with the next module in order to boost up all the systems so that we can really control these things.
Perfect. And like the error correcting codes that you have is also for non-Clifford gates, or?
Yes, this we have, that's right. Now for the specialists here, we need Clifford gates, but we need, in addition to that, Clifford gates is essentially the class of Pauli operations that we have. But we need also the magic gates, so this is T gates.
T gates.
T gates will be injected. We have a procedure for T gate injection. We can do this with fidelity of beyond 96, 97% right now, so this is done, and this can be done. You don't need a so-called T-gate factory. This can be injected, so this is not too much of an overhead. But the error correction includes that, because we just have a fault-tolerant way of including this and checking on the way that error propagation doesn't happen. So this works.
Perfect.
These things work in demonstration experiments for each individual group. But now the point is, you have to put this reliably together. But then the next step comes. Now you have one module of, say, 1,000 qubits that maybe comprises then several 10 logical qubits, and you want to interconnect that with the next module. Then you want to make sure that the error correction, of course, goes between the two modules, so these things explode. So it's just a step-by-step procedure. That's why I said in the beginning, yes, technologically this is doable. I don't know exactly to which degree. The best way would be that a young student comes up and she tells me tomorrow, no, I have a better idea. Let's do this. Graphene is just a layer. You just take a little tape it off, get a single layer. That Nobel Prize idea, that's necessary to get for the next step.
Thank you. Thanks a lot.
Okay. If there is more question or comment, before concluding these things, let me remind you about the structure of also of this type of EQ and BASQ events. Is that there is the scientific talk that is doing now Rainer here in Bilbao, and then there is a popular talk that will be tomorrow in San Sebastian, in Donostia, in Tabacalera. So obviously all of you are invited also to this other event in Tabacalera tomorrow. But now let me thanks again Rainer for this really nice colloquium. Thanks a lot.